Hello, so my previous video started with definition of metric spaces and how most of the spaces we have seen in our mathematical life are metric spaces in one way or another. In particular, we saw that Hilbert spaces and Banach spaces are examples of metric spaces. Anytime you have a norm defined on a vector space, you can use that norm to define a metric on that space. And I want to continue with some more examples of metric spaces just to emphasize further how diverse they are and how universal the methods of studying them should be, which just adds to their usefulness, because if you end up proving some result about metric spaces in this generality, then the applications of that will be just as universal. So some more concrete examples first that we have seen. The space of all continuous functions on a space X. For instance, if you take a compact interval in R, then you can talk about the set of all continuous functions on that interval. And we have this supremum norm that you should have seen that actually quantifies the notion of uniform convergence. And then there are the spaces of sequences, which we denote by little lp. And P appears in the way we restrict to those sequences for which the sum of pth powers converges. And if we take 1 over p root of this summation, that is the LP norm. And again, because it's a norm, we can turn this space into a metric space and then ask a lot of questions about the metric geometry of that space. Is it complete metric space? Is it separable metric space? And so on. The capital LPX would require some X on which some measure also is defined, so that we can define the set of those real valued functions that are LP integrable, literally that their pth power is integrable. So with these more familiar examples out of way, let's talk about Hausdorff distance. So this is an amazing metric that compares any two compact subsets of, say, Rn. And that is basically telling us how distant two shapes are. So let me move to my Wikipedia pages, which I will use extensively throughout this presentation. So there is a blue line and there is a green line. Both are closed curves, and we want to compare how distant these two shapes are. And here are formal definitions and whatnot. So basically, you want to shift and translate them to reach the infimum distance between pairs of points. But and you can imagine the applications would appear in computer vision and computer graphics. So this last line reads in the application section that in computer graphics, the Hausdorff distance is used to measure the distance between two different representations of the same 3D object, particularly when generating levels of detail for efficient display of complex 3D models. So the next example, again, I want to go back to finite metric spaces, a finite collection of points with distances between them that satisfy the triangle inequality. If you think that they must be easy metric spaces and trivial or boring, then think again, because with only 4 points, you can create a metric space that you cannot embed into any Euclidean space. So we have 4 points. I want to let the distance between these two to be 4, distance and all other distances to be 2. So you have 2, 2, 2, 2, and distance between these two also equals 2. You can check that actually triangle inequality holds with any 3 of them that you choose. So it is a metric space, but this metric space cannot be a subset of any Euclidean space. In any Euclidean space of any dimension, you cannot find 4 points with this configuration of distances between them. That's an easy, not an easy, but an interesting exercise. Basically, this point has to be the midpoint from this midpoint of this line, and there is only one such middle point. Now we're claiming that there are 2 different middle points to the same line segment, which cannot happen in Euclidean spaces. So already with 4 points, you have a metric space that is not embeddable in a metric space. Then you can imagine many applications where you have a finite bunch of objects with distances defined between them, and to study that, to embed it into some Euclidean space, you may ask about the optimal ways you can embed them in a Euclidean space. You preferably want the smallest dimension of the Euclidean space required. You may also, well, this space doesn't embed, but with some distortion of the distances, you may be able to do that. You may ask for the least amount of distortion that you have to pay so that you can embed it in a metric space. So I'm going to talk about 2 concrete examples of finite metric spaces. So one of them is what we call the Hamming distance. So Hamming distance is defined between strings of same size. So let's say here we talk about 7-letter words, and Caroline from Catherine is 3 distant. So the distance between the 2 words is 3 because you need 3 substitutions of characters to get from one to the other. And this could be done with letters as well, or with combination of letters and numbers. So basically any alphabet you have, then you can define distance between strings of same size. So same size here matters. If you do not want to restrict to same size strings, you have another distance which also includes addition of letters or deletion of letters without replacing them. But the applications of this Hamming, even in this simple case, the Hamming distance is to information theory, coding theory, cryptography. So you can use distance to see how well a code is able to detect errors, for instance. So the other distance that I said is more general, is Levenshtein distance, as you can see here. Okay, so the other finite metric space that I have in mind is this graph-headed distance. Well, this is not a finite metric space. The space of graphs is not a finite set, but what I mean is there is some combinatorial and discrete flavor to all of this. So you want to measure how distant, how dissimilar or similar 2 graphs are. And to measure the distance between 2 graphs, you define a set of allowed operations on a graph. For instance, you can insert a vertex, you can insert an edge, you can delete an edge, you can substitute an edge, which means changing its label or its color. And you can say what is the minimum number of these operations which will get you from one graph to the other. And again, you can think about applications. For instance, here, handwriting recognition, fingerprint recognition, and something called chemoinformatics, which applies methods of information theory to study of chemistry. So all cool stuff. Already in finite metric spaces, you see a lot of nice applications. Now, this geometric group theory here is a whole universe in itself. So the core idea is as follows. So we call a group, which is a set with multiplication, a finitely generated group if you have a finite bunch of items, say A, B, C, and D, such that any element of group is constructed out of multiplying a finite number of them. So hence the word finitely generated. So A, B, C, D here will be the generators, and then every X will be generated by certain multiplication of these. So maybe you multiply 3 B's here, and then you multiply a C, another A D, maybe you end with B. And for Y, you will do maybe 2 A's and 1 B, 1 D, maybe 3 more A's, and finally another B. You can easily convince yourself that you can get from any X to any Y by, again, a finite number of multiplications into elements from this generator set. And then you can define the distance of X to Y to be the least number of these multiplications that get you from X to Y. That can also be visualized in terms of graphs. So here is a group generated by two elements, A and B, which is easier to represent here. So multiplying by A is going with the red arrows, and multiplying by B means going by blue arrows, which are vertical. So from any point in this graph to another point, you can get by certain number of multiplications of A and B's in various orders. And the distance will be exactly the number of edges you take to get from one to another. So this is called the Cayley graph of a finitely generated group. Anyway, what happens once you put this metric on a group? You started with a group, now you ended up with a metric space. There are well understood questions in metric world, and there are some nice questions in group theory. So if we can study some algebraic questions from group theory in terms of corresponding questions in metric theory, then that bridge can provide a whole lot of fascinating collaborations. And that is exactly what happened, and this work was pioneered by Gromov. And here you see a long list of applications and what is called here themes in the study. And these are pretty recent, so you can see it's 1990s and 2000s. For instance, there are certain algebraic properties that are invariant under quasi-isometry. So quasi-isometry is a purely metric notion, and then, for instance, you say that the growth rate of a finitely generated group, it remains the same if it is quasi-isometrically transformed. Or you can say if two groups, the corresponding metrics for two groups are quasi-isometric, then they have the same growth rate. So you can use this piece of information to distinguish, say, two groups. And this is not an area where I have done serious research in yet, so I cannot provide more, but it is just amazing thinking about how study of groups ended up having very, very intimate relationship to study of metric spaces. So I not finding it at the moment, but somewhere here we read that the study of finitely generated groups has been kind of hijacked by this metric approach. So actually I found it here. So currently combinatorial group theory as an area is largely subsumed by geometric group theory. So that probably wraps it up that these methods of metric geometry just came in and made a whole lot of difference to this area. Now, these, again, the examples we saw above had this combinatorial and discrete flavor to them. The area where I am more familiar with is when you have some sort of continuum and you leave the discrete world. Of course, Euclidean spaces and all those other larger LP spaces that I mentioned above fall in that category, but if I look beyond the obvious examples, I can mention fractals. So, for instance, we have the cock snowflake where you start with a triangle and you break edges and add some new edges, and you do it infinitely many times, just like when you construct counter set, for instance, and you end up with some space which we call the cock snowflake for obvious reasons. Then this is a metric space because it's a subset of R2 and it inherits the distance of R2. There are many interesting questions about these spaces, and they break our intuition from Euclidean spaces. For instance, although the distance between any 2 points is well defined as a real number, the path from one point to another is always infinite. So if you take two different points on this manifold, it's not definitely a manifold, I mean on this object, there is of course some continuum between them, but the length of that is always infinite. So in other words, you cannot actually move with finite speed along this curve. But still, there are many interesting analytic questions you can ask. For instance, we will later see that you can talk about Sobolev spaces on such objects, and you can talk about their dimension, and many other interesting questions, and the methods of Euclidean world will no longer apply because no piece of this set is actually a copy of R1 like manifolds are. So a usual circle is easy to study because locally it is just R1, and any analysis you have learned from R1 like derivative integration just upgrades to working on S1. But with such spaces, it is no longer available, and we enter the true world of metric spaces. So there are Julia sets coming from complex analysis and dynamics, which also can be studied and have to be studied by methods of metric geometry. And finally, I want to talk about, just mention Subramanian geometry, Carnot groups, in particular the Hessenberg groups, I should say, where they have some common features with Euclidean spaces. They are Lie groups. There is a notion of addition and multiplication, but they are non-commutative, so multiplying AB is not always the same as multiplying BA. And they have dilations similar to the scalar multiplication of Euclidean spaces. However, we construct metrics on these say, Hessenberg groups that are far more different than the how distances and metrics work on Euclidean spaces. For instance, if this is H1, the first Heisenberg group, you define distance between 2 points, say here and the origin, as the shortest path between the two. However, here by path, we mean only certain path whose velocity vectors always lie within a restricted plane. So at every point of this space, you have a 2D plane, and a path that is allowed in computing the distance has to have the velocity vector lying inside this 2 plane. But when you move from one point to another point, this plane changes its angles, and there are so the twists and turnings of these planes from one location to another allow you to still connect any given points, although you are only restricted to certain directions. So here there will be, the path will end up actually going around the t-axis. So the shortest curve will not be just going vertically up, because the velocities actually along this z-axis, the velocities have to be horizontal. They have to exactly be parallel to the xy plane. So going vertically up violates that condition that we require the velocities to lie in these planes. So you have to take off parallel to xy axis and then use this twisting of the planes as you go up, so that you can make turns use in the velocity and end up at some other point. So anyway, there are some conditions on how these planes twist that make it possible to still connect any 2 points by some curve. And then you look at the shortest curve under these conditions that connects 2 points, and you call that the distance of 2 points. So this H1 is really actually modeled on R3. So it's R3 with a new distance, and this distance is pretty wild and different from Euclidean one. For instance, here, if you are connecting to 0, 0, and t, from 0 to 0, 0, so the Euclidean distance would be just t. However, in the Heisenberg group, that distance is actually root of t, which is way bigger than t if t is small. So this shows that the t-axis is actually much longer in the Heisenberg group than it would be in the Euclidean case. And again, you can begin asking many questions about these spaces. What are these exact shortest path? How are they characterized? Can I talk about Sobolev spaces on these spaces? And what is the dimension of this space, the Hausdorff dimension? So we will hopefully get to all of these interesting questions, but for now you should please tolerate me going over examples, basic definitions, because we have to make sure that we are on the same page. And also, if we get into details and the specific constructions, we may forget why we are studying metric spaces in the first place. And at that point, I want to remind you of all these examples and say, hey, look, the tools that we are building have so many diverse applications, and that justifies the study of metric spaces. So I will have a couple more videos of this nature, but then I will switch to computation of Hausdorff measures, and we will see from there where we can continue. Have a great one. Thanks for watching, listening today, And please subscribe if you haven't, because that makes a difference on my end.